Okay, no problem. Now I hope I've got this right. I hope you can see my screen there, but
yes, we can. Yes.
Okay, great. Good, thanks. So I'll just start with a bit of an introduction about myself. So I'm at Lancaster University now. I've been there about 6 years, where we started up a new astrophysics group. And before that, well, I've done several postdoctoral positions. I was in Hawaii for a bit, working at the Gemini Observatory, which was very nice. I worked at the ESO, which is the European Southern Observatory headquarters in Germany as well. And some of these things will all sort of link into the talk I'm going to give. But most of what I'm going to talk about is about this study of these distant supernovae, and that's work I did mostly when in my first postdoctoral position in Berkeley in California, where I was working with Saul Perlmutter's group, and that turned out to be very interesting, and I kept on working in that field all the way through and still am. So maybe I'll just get started then. So this is a talk, actually, it's very similar to one I've given a few months ago now for the Institute of Physics and the Manchester Lit and Phil Society. So I hope not too many of you were there for that, because it will be quite similar. But I'll go ahead anyway, because I think it's a fun topic. So this image I'm showing here is the Rubin Observatory, which is being built in Chile right now. And it's the telescope is not complete inside that dome there, but it's getting there. And this is going to be absolutely transformational for this particular topic, because it's a very wide angle, very wide field of view telescope, but also a large diameter telescope of about 8 meters. And that's quite an unusual combination. So I'll come back to that right at the end about how this is really going to change our view of supernovae and dark energy. All right, now, can I advance my slides? That's the next problem. Yes, there we go. Right, so dark energy then. So this is a huge mystery in physics. I think it's probably one of the biggest problems that faces physics overall at the moment. And it is really trying to explain what it is that's causing the expansion of the universe to actually be speeding up. So this observation that the universe is not only expanding, but expanding at a faster and faster rate was a very big surprise. And I'm going to describe how those observations were made. And we just don't understand why it's happening. So on the right here, this is a kind of schematic of the timeline of the universe, if you like. So that down at the bottom here, and let me just see if I can turn on my laser pointer. That's the next challenge.
We can see your arrow on the screen.
Oh, okay, that'll do then. I'll use that. Let's just get rid of that. Thank you. Okay, so yeah, down in the bottom here is if that's the Big Bang. The way this is drawn is that the universe expands very quickly from that point and then starts to kind of coast.
I'm sorry, Isabel. We can still see your pointer. Yes, beg your pardon.
Maybe I have to keep moving it. Okay.
Yeah.
So in this period of time, the universe is kind of it's still expanding, but at a slower and slower rate because of the matter inside the universe kind of starting to pull it together. But then sometime around here in time, which is about where we are actually, the expansion actually started to speed up against the pull of gravity. And we don't understand this. And it's that mystery that's really the big problem for physics now. What is causing this kind of anti-gravity behavior? And so we don't know what it is, but it's been given this name, dark energy, which is just a sort of general name for the thing that we don't understand that's causing this phenomenon. So we don't know what it is, and we just call it dark energy, and that's what I'm going to call it all the way through this talk. So the basis of this, of the original measurements, was made by well, let me sort of step back. So I want to try and explain now how those measurements were made. So what we needed to do to measure this acceleration rate of the universe is to measure how big the universe was at different times in its evolution. And then you can kind of look at the rate at which it's grown, and in fact, the rate at which the growth changes, and that's the acceleration. So these three balloons here are supposed to represent the universe at different times as it's expanded. So the whole thing has got bigger. So the space between galaxies has expanded, and that means that the distance from us to every other galaxy has expanded. So what we need to do then is measure if we're going to go about measuring the acceleration rate of the universe, we need to measure the universe's size at different times. And it turns out that measuring the relative size is actually quite easy. It's the time part that's tricky. So for size, we can just use the redshift. You've probably come across the term redshift, and it's quite often explained as a kind of Doppler shift to do with the rate at which things are receding away from us. But actually for cosmology, when you're talking about these huge distances and talking about the universe as a whole, it's more accurate to think of redshift as an actual stretching of light. So if you imagine a light wave traveling across a balloon now, this balloon sort of analogy now, and we expand the balloon, you can see that the wavelength of the light as it travels gets stretched as well. And that means that it shifts all the colors of the radiation that we see towards the redder end of the spectrum, which is why it ends up as being a redshift. And so actually it's incredibly direct. If you can measure how much the light wavelength of the light has been stretched, you've got a direct measurement of how much the universe has expanded in the time it's taken for the light to travel from a distant source to us. And I think that's really amazing. So this is a few examples of some measurements of redshift. So this is 5 different galaxies here. This is their spectra. So looking at their intensity as a function of wavelength. Oh, sorry, Alex, I'm just giving a talk, sweetie. Thank you. Can you just close the door? That's my son popping in. So these spectra, they show these characteristic features at certain wavelengths, like here, for example, this is a hydrogen alpha line, more hydrogen lines and oxygen lines. And you can see that pattern being repeated in all the galaxies, but at different wavelengths, because the whole pattern is shifted towards the red in some of them compared to others. So as you get to go down the diagram here, you're going to higher redshift. So the higher redshift galaxies will tend to be the ones that are further away. Their light has taken longer to get to us. And while that's been happening, the universe has actually expanded so much that the wavelength that we observe is a longer wavelength than it was when it set off. And we can just directly say, so this one at the bottom has a redshift of nearly 0.4, which means the expansion of the universe is a factor of about 40% in the time it took the light to travel to us. So very, very easy to measure this relative size thing. We just use the redshift. The problem comes when you try and measure the times. So what we really need then is what time was it in the universe's history when the light set off? And then if we can do that, we've got measurements of the size of the universe at different times. And so to do this, we need the light travel time. But this is a difficult thing to measure because really it's effectively, we need to know the distance to the thing that we're observing. And measuring distances, I'm sure you know, in astronomy is really difficult. So just as an example, here's a lovely image from the Hubble Space Telescope, ultra deep field. There are lots and lots of galaxies in this image. And we can't really tell which are the distant ones and which are the nearby ones. I mean, you might think, well, the nearby ones are the bright ones, and you'd probably be right on average. But it could just be that that one, for example, is very bright and really, really far away, but just intrinsically extremely luminous. And it could be that these little faint ones are they could be really nearby, but just intrinsically very faint. And we just don't know. We need a way of measuring distances. And so what we need to be able to do that are standard candles. So these are objects where you know, for some reason, you know their intrinsic brightness. And if you have a class of objects like that, then you have a way of measuring a distance, because you can just look at how bright they appear on the sky. And then that does tell you the distance, because you've removed this uncertainty about how bright it is intrinsically. So I'm going quite fast here, but what we're trying to get at then is that we need this class of object where we know the intrinsic brightness as a way of measuring distances. And it turns out that type 1a supernovae are excellent standard candles. So these are 2 movies here. I'm going to start them going. About possible ways that a type 1a supernova explosion can happen. So what we believe they are white dwarf stars that are being tipped over this critical mass limit of 1.4 times the mass of the sun, known as the Chandrasekhar mass limit. And when that happens, the electron degeneracy pressure that's holding a white dwarf star together can no longer support it, and the whole star is disrupted. And there are various ways that a white dwarf star could be pushed over that limit. One is taking matter from a companion, which was the top movie that I showed, and it's just about to start. There we are. So this is a white dwarf star in this animation, taking matter from a companion, and that will gradually push it over at the 1.4 solar masses limit that makes it explode. Another possible scenario is that you've actually got two white dwarf stars orbiting each other and they merge, and again that will push the combined object over the mass limit that will cause an explosion. So the idea here is that because these white dwarf stars always explode at this 1.4 solar mass limit, and they're completely disrupted, that means the energy released in that explosion should always be basically the same amount, which means they're a standard candle. It means they always have intrinsically the same amount of energy released. They should be the same brightness intrinsically. And so if we can measure them, how bright they appear on the sky, that should give us a measure of the distance. And so that gives us a measure of light travel time. So now we've got time. And remember, if this supernova explodes in a galaxy and we can measure its redshift, we've got the size of the universe as well. So we've got all the information we need for that object to measure the size of the universe and the time. And then if we have a whole load of these type 1a supernovae, we can map out how the universe's expansion evolved. So that's how we can measure its acceleration. So that's actually that's probably the most intense bit of the talk. I hope that's not gone too fast, but the rest of it is mostly about the observations and the kind of how the results emerged. So obviously the first bit of all this, we've got to find supernovae, and so there's various problems with that, and you're probably aware of this as observers yourselves, that if you want to find a supernova, we've got some problems. First of all, they are unpredictable. We don't know when they're going to happen. We don't know in which galaxies they're going to happen. They're pretty rare. So typically one supernova per 100 years per galaxy. So it's not much good just watching one galaxy and hoping that you're going to get a supernova. You'd have a very long wait. And they are faint. The distant ones that we need for cosmology are a long way away, so they're not easy to spot. So those are the main problems. And I think the real breakthrough in this whole field came when the digital detectors for astronomy got large enough that you could observe a very large area of the sky in one go. And that then increases the chances of there being one galaxy in there somewhere that produces a supernova explosion. So that's really what changed. I think it was really a technological breakthrough, really. And obviously the understanding that how that could be applied to astronomy. But just as a little aside, another way of finding supernovae was demonstrated very nicely by Bob Evans, who was an amateur astronomer in Australia. And he actually found 40 supernovae using just visually. And his method there was to just memorize galaxies. So this is actually one of his discoveries. This is a digital image taken with a professional telescope, but he wasn't doing it this way. He was actually memorizing galaxies, going back and visiting them regularly, and just noticing when they look different. If a supernova had occurred, a little spot would appear much brighter, and so he would be able to alert the rest of the astronomical community that a supernova had gone off. And in this particular case, it was then followed up by professional telescopes. So that, I think, is an amazing achievement and not something that's easy to do at all. So the way, I'll just skip that slide, but the way we do it for this project and most commonly now is to, as I say, observe quite a large area of sky with digital detectors and then subtract images. This is actually two images of the same patch of sky and they're blinking. I don't know if you can see the difference there, but something appears in the middle. And that is a tiny increase of light due to a very distant supernova. And I'm afraid that's the most dramatic images we can get of the sorts of supernovae that we're talking about now. They're so far away that they just don't look particularly exciting, but that is a distant supernova. And there's probably a galaxy under there that we just can't see, that's too faint. So we typically take an image, take a second image of the same patch of sky. This is now a zoom in of quite a much larger area, and subtract one from the other. And that, if everything goes well, all the non-varying objects in the sky will subtract out very cleanly, and you're just left with a little spot there at the position of something that's changed, which might be a supernova, but sometimes it's not. It could be an asteroid passing through or various other things that contaminate our surveys. So that's the basic idea of how we find distant supernovae. Then there's quite a lot of other things that we need, other bits of information, which relate to what I was saying at the beginning of the bits of information we need. So we need, first of all, we need to be sure it's a type 1a supernova, not something else. And the way we usually do that is to get a spectrum with follow-up observations. So this is an example spectrum of a type 1a supernova. It's quite noisy because it's distant. And we'd look for these characteristic wiggles that happen at particular wavelengths. And this particular feature, actually, this little faint dip here, is the characteristic sign of a type 1a supernova. So that's the type. Then we need the redshift that I mentioned. So that's how we know the size of the universe when the lights set off. So the relative expansion rate, the relative expansion from the time when the lights set off to now. And from that we use these narrow emission lines in the spectrum of the galaxy. So that's what's shown here. These little very narrow spikes are real features. They're not noise due to particular elements in the spectrum of the galaxy. So we can measure a very accurate redshift from something like that. And then we need the distance. So we need the brightness of the supernova as we observe it. And for that, we measure the supernova as it brightens and fades away. And then we have to try and catch the peak magnitude. So it's the peak that's the standard quantity right at the top. And so obviously to do that, you need quite a few measurements of the supernova so that you can get a good measurement of where the peak is and how high it was. So there's quite a lot of observations involved here. And these observations have to be made for every supernova we find or that we want to use for cosmology. So it's obviously quite an investment of telescope time, and telescope time is expensive. So there had to be, when this whole idea to try and measure the acceleration of the universe started up, there had to be good motivation for doing it. So I'm going to try and explain that motivation now by going back to when this experiment was kind of devised, and just explain what the motivation was for the group doing it at the time and where things went after that. So why bother making all these observations then? So this was now going back to the early 1990s, when the Big Bang model for cosmology was well established. And at that point, the idea was that in this sort of diagram of the size of the universe against time, you'd have a Big Bang at the start, and that would set the universe off with some speed of some expansion rate. And then if you believe that the universe only contains matter, which is what they thought at the time, there's really only three things that can happen then. So the universe can either collapse back on itself because gravity will pull it together. So this is a bit like throwing a ball up in the air. If you throw the ball up, as long as gravity is strong enough, the ball will come down again. That's that sort of idea. Or you can imagine a case where perhaps gravity isn't weak enough, so there's less matter there, in which case the universe will expand, but it will never actually collapse back on itself, but it will slow down. Or there could be something just in between where you throw your ball up and it doesn't quite fall back because gravity is not quite strong enough, but it doesn't disappear either, and it just ends up exactly staying, asymptoting to basically staying at the same distance. And that's a kind of critical imaginary point. And I've labeled these with the symbol we use for cosmology in this case, which is telling us about the density of matter in the universe. It's called omega matter. And it's all measured relative to that critical point. So a large amount of matter, omega matter larger than 1, gives you the collapsed universe, and omega matter less than 1 gives you the universe that expands forever. So if there's only matter in the universe, you can only be on one of those three scenarios, really. And for various reasons, a mixture of theory and observations at the time, the kind of critical value was the one that was favoured. So people believed that, that the universe had exactly the right amount of matter. It's kind of nice theoretically. It would just make the universe eventually stop expanding, but not collapse back. Now, there were problems with that. So just before I go on, there were problems with this omega matter equals 1 universe, with this perfectly balanced universe, if you like. It gave the wrong age for the universe. People have already started to find stars that were older than the age of the universe that you should get for that particular set of parameters. There were other things to do with the clustering of galaxies that didn't make sense. So there's a bit of discomfort with this idea, but it seemed to fit most of the observations at that point and was nice theoretically. And you'll see in all of these three cases, you would expect that the universe is decelerating, which means that it's always slowing down. And that's just because of the matter in the universe being pulled together by gravity. Now, so the idea was, because there was these problems like with the age of the universe and things like that, people decided, let's go and measure this deceleration rate and see which of these curves we're on. So they wanted to collect a set of points. Again, you could use supernovae to do it, to measure the size of the universe at different times and decide which of these three we're on. So that's the plan. And so the Supernova Cosmology project was set up. This was led by a group in Berkeley by Saul Perlmutter, who I mentioned earlier. This is him here. This is Gerson Goldhaber, and I'll mention him later as well. They actually came from particle physics background and approached this very much like an experiment. So they wanted to go out and do an experiment in the and do all the proper statistical analysis in the way that you should do for a proper physics experiment. And so they were setting out to measure the cosmic deceleration, because everyone was expecting the universe should be slowing down. And this is one of the telescopes they used, the Isaac Newton telescope in La Palma. And they came up with this nice idea of how to do the experiment. And this is quite a busy plot, but I'll sort of go through it very quickly. So the idea is that you take a set of observations when the moon is dark. So you take you essentially tile quite a large area of sky with a large detector to get, just doing images, to get lots and lots of galaxies in those images. And then you wait for about 3 weeks until the moon is dark again. And in that time, that's just about the right amount of time for a supernova to have reached peak brightness. And then you take another set of images and then you subtract them and look for places where the supernova has got, where a supernova has appeared. And then you can start doing the follow-up observations that you need, like the spectroscopy to get the redshift, and more imaging to get the rise and the fall of the light curve here to measure the peak brightness. And this was done, this was all planned out and done at various telescopes around the world, which are all shown here. One in Chile, one at Keck Observatory. I'll come back to this later. That's in Hawaii, all sending their data back to Berkeley for analysis. So the real clever thing about this was the fact that because they'd got such a large area, they could guarantee they were going to find supernovae on a particular date, which was this second set of observations. So it's taken away that whole problem with the unpredictability, because there were such a large area being surveyed, you could guarantee it. So you could schedule in advance follow-up time on big telescopes, which you normally have to book years in advance, or at least 6 months in advance. So you could have it all booked and ready to go, and you'd know you'd have some supernovae to follow, and that was great. So that means you could start finding batches of supernovae on certain dates. So the first supernova they found was in 1992, called 92Bi, which is a very imaginative name. And this was the most distant type 1a supernova known at the time, with a redshift of about 0.5. And it really was a proof of concept. So it showed that they could find supernovae on a particular date, and they got all the observations they would need to do cosmology, and wrote a paper about it called a supernova at redshift 0.458 and implications for measuring the cosmological deceleration. So we're still talking about deceleration at this point. It's funnily enough, the results from this supernova did come out quite interesting, they found a low value of deceleration, lower than expected, but the error bars from just one object were too big to really say anything conclusive. But it probably was a hint that something interesting was there, actually. So then, over the next few years, the group started to do coordinated searches using more than one telescope, and that was just a way of getting more observing time, really, and got the sample up to 7 supernovae. And then in 1994, I joined in the whole thing. I moved to Berkeley for my first postdoctoral position and joined Saul's group, which I think I was extremely lucky to do. And about the same time, another supernova search group formed called the High Redshift Supernova Search Team, led by Brian Schmidt and Adam Rees. And they'll appear later as well. So this was very interesting, actually, because they were astronomers, and so they could get going really quickly compared to the Berkeley group, which were mainly particle physicists who'd switched fields. So it was a really different way of working and a really interesting kind of competition, because that's what it became. And in about 1995 onwards, both teams started using a different camera. So instead of the Isaac Newton telescope, they switched to using the Cerro Tololo telescope in Chile, which had a bigger field of view, better weather conditions, everything going for it. So there was this very interesting phase when we were both teams were working on the same telescope. We'd see each other, we'd have our nights, and then they would have theirs, and we'd swap over and see each other in the canteen and everything on the handover night. So I don't want to say what we found, but it was quite exciting, and you could see that it was going to get interesting. And these are some of my colleagues from our team, Peter Nugent and Alex Kim. These are the observatory vehicles at the time, going back a bit, but they had a fleet of VW Beetles as their observatory cars, which was nice. And this is a bit of an astrotourism, really. I'm just showing you some of my snaps from these trips, but this was when we went down to use the CTIO telescope in Chile. It's a beautiful site. You can see how it's just fantastically clear, a very nice telescope to use. And actually most of my sort of input to all this was doing the spectroscopy. So I got to use the Keck telescopes in Hawaii quite a lot. So this is the summit of Mauna Kea in Hawaii, which is very high. It's at 4,200 meters. And you certainly feel that when you're up there. And these are the 2 Keck telescopes, both 10-meter diameter telescopes. So these are the largest telescopes in the world. And this next to them is the Subaru telescope, which is a Japanese 8-meter diameter telescope. We didn't actually use that one. Not for this, not at the start anyway. So yes, as I mentioned, this is a very high site, so you really feel the altitude when you're working up there. And after a few years, they set up a very nice remote observing facility in Hawaii, in Waimea, which is actually in the wet side of the island. So it's a bit foggy. So it's quite strange observing here, because the good thing is you have to travel to Hawaii still, so you get to do that. But then you're sort of quite often sitting under a cloud like this in this very humid atmosphere, whereas the telescopes are above all the clouds and the mountain in perfect, clear conditions. It's a strange business, but actually a lot more pleasant observing there than it is at the top. And this is one of my pictures that I took on the first trip, when they were still building the second Keck telescope, and the Subaru telescope was also being built. So the spectroscopy, that was to get the redshifts, remember, and we were finding the supernovae and measuring their brightnesses at other telescopes, and eventually got to the point where we had about 40 supernovae, and that's then enough to start finding the results for cosmology. And this is where it really got interesting. So this image, so if you remember when I said that we found, with that first one that they found, they were already able to measure a sort of value for the matter content in the universe just from one object, but with very large uncertainty, just from its peak brightness. And you can actually do that once you've got a sample large enough, up to about 40, you can start plotting them on a histogram of number against the matter content of the universe on the x-axis. So each of these big sort of centimeter sized squares is one supernova, and you can see how they sort of stack up. So here's our value of 1.0, That was the value everyone was expecting to get. And funnily enough, the first 7 supernovae, which are shaded here, kind of agreed with that. But as the sample got bigger, the distribution changed, just from statistics, presumably. We're just unlucky with those first 7, but the peak is somewhere around here, is nowhere near 1. It's more like, you know, 0.1 or 0.2. So that's really the sign something very strange is happening. We're not getting, there's not enough matter in the universe. And certainly if you believe that the universe is flat, which is just means that total energy content in the universe is 1, that means there must be something else making up the content of the universe. So we were getting a very low value of omega matter. And in fact, if you calculate the deceleration of the universe, it came out negative from these results. So negative deceleration means acceleration. And that was the first real sort of realization that the universe's expansion could be accelerating. So obviously this was presented in a group meeting we had, and it wasn't really a surprise. We knew there were funny things going on in the data, but at that point things really sort of hotted up, and we had to be absolutely sure this was right, because this is a very big result. And so lots of checking went on, but at the same time, you know, we want to be sure it's right, but there was a competition. There was the other group as well doing the same thing, and we knew that they were finding the same thing just from informal conversations. So this race really got started, and it was very intense and very exciting. So this is one of our group meetings this was in Paris actually, where at this point, and I remember this very well, the sort of intensity of very long days checking every little detail. And this is a little staged photo taken much later, once everyone was friends again, and it was all, we knew that the results were right. This is Saul Perlmutter on the right, and Brian Schmidt, from the leader of the other team, on the left, having a friendly battle at the Aspen Center for Astrophysics. But it wasn't quite so friendly earlier on, when we didn't know who was going to be first to get the results out. So actually, in the end, the other team beat us to it in terms of the getting the results out, but we were very close. And the main thing was that they did agree extremely well. And so this is our paper, Perlmutter et al. Paper. And I just show you the actual plot from that paper, the actual result. So this is what's called a Hubble diagram, which is plotting the brightness of supernovae on a sort of backward scale, so fainter going upwards, and the redshift in this horizontal axis. These nearby supernovae are not part of our study. They kind of anchor the diagram, but what we're interested in is what happens up here at higher redshift. So these are our data points, the 40 or so supernovae. And then overplotted, these lines are various kind of expectations for different content of the universe. And the second to bottom line, I don't know if you can see my cursor now, but the second to bottom line is the one you would have expected if there's only matter in the universe. So you can see kind of by eye that the points are all above, well, not all, but certainly on average, those points are above that second to bottom line. So that means the supernovae are fainter than you would expect, which really means they're further away. So something has made the universe bigger than we expected.
Yeah.
So as I said, this implies, is everything okay?
Isobel, can I stop you a moment?
Sure.
Mahir, can you turn your microphone off, please? Thank you. Please carry on. Okay,
no problem. Yeah, so as I mentioned, this implies if we well, you can actually sort of see it here, that you can make the data fit one of these models, one of these expectations, if you put in something else. And that something else is labeled lambda here, which I'll come to in a minute, but it's essentially something else that acts against gravity. So anything with gravity in it will tend to pull the universe together, which is the opposite of what we need to explain these data. So we need something that is pushing the universe apart to fit the data. And in fact, about 70% of the energy density of the universe has to be in that component. So the dominant component of the universe has to be this sort of anti-gravity component. So this is really weird. So if I just go back to this sketch, this red line now is what that means for the history of the universe. So it's, you know, imagine throwing your ball up in the air and it just starts to slow down, but then just takes off. And so we don't understand it. And on the good side, though, it does solve several other problems. So it does happen to solve the age of the universe problem. So a universe that with this component in it, if you extrapolate back now from our current point, would have been old. The universe would have been older. So that does solve the problem that some of these very old stars in the universe can now exist. So that's good. And it actually turned out, you know, most other observations then fit in very nicely. And it actually, you know, you probably know, but these results were awarded many prizes. One was the Gruber Prize. That was the first large prize to be awarded. And then the big news was getting the Nobel Prize for Physics in 2011 that was awarded to the leaders of the groups, Saul Perlmutter, Brian Schmidt, and Adam Rees, for the discovery of the accelerating expansion of the universe through observations of distant supernovae. So this is great, but you'll notice there's no mention of dark energy or anything to do with the explanation. The prize was awarded for the observations that the universe is accelerating. And this is great. So Saul and the other leaders of the other group as well, really nice people. They invited their entire teams to the Nobel Prize ceremony. So I've got a few pictures of that as well. It was marvelous. And so this is the Swedish royal family here and members of the Royal Academy of Sciences in Sweden. And there's an orchestra up here. And so these are the Nobel laureates here, and they will give an acceptance speech at this event. But there's actually a whole week of events going on, and there are nice talks and kind of social events. And one of the nice things is that they get the students of the University of Stockholm involved, so they get to meet the Nobel laureates and sort of show them around. So it's a really nice atmosphere. I've got a few more pictures here, but this is the main evening of the prize ceremony, and this is one of the other events. There was a ball as well, another evening. So it was wonderful. So this is great. So we've got sort of measurements of this acceleration, but what is actually causing it is now the big question. So the last bit of my talk is about this and what we're doing to try and find out what's causing it. So we've got this unknown component. We just called it dark energy, and for want of anything better, really. So one possibility of what's causing it is that it's just the cosmological constant, which is sometimes called lambda. And this is a mathematical term that was introduced by Einstein in his field equations because he thought that the universe was static. But he knew, of course, that gravity would tend to cause the universe to collapse. So to make it static, he put something in to sort of counteract that. And it's just like a kind of constant of integration, if you're familiar with that, but it is just a constant in his equations. But when he found out that the universe actually isn't static and that it's expanding, he thought he'd made a huge mistake by putting this into his equations. He called it his biggest blunder. But strangely, mathematically, it perfectly fits the observations that we're making now, this sort of something that counteracts the pull of gravity. So it fits really well, but there's no real theoretical reason for it. It's just a constant, just mathematical constant that's been put into some equations. So what possible physical explanation is there? And this is where the real problems come in for physics generally, that there are ideas for what could cause something like this, some energy in the universe, but perhaps caused by particles or energy fields that are associated with them. But anytime you try and calculate what sort of energy level you should get from that, it comes out way, way too big, 120 orders of magnitude too big. So there's a real problem there. And that's not the only problem, actually, but that's the biggest problem. So now the big question is, what else could it be? Is it just that, is it lambda? Is it the cosmological constant? And if so, what's actually physically causing that? So perhaps another explanation is it's not a constant everywhere. It's something a bit like what happened right in the very early universe when there was this period of inflation. Right after the Big Bang, there was this rapid expansion. So perhaps it's something like that. Or could it just be that actually general relativity isn't the right theory and our theory of gravity isn't quite right? So perhaps that's the answer. And So this is a massive area for theoreticians at the moment, all sorts of interesting theories coming up. And from the point of view of an observer, I think the best we can do on our side is just to make better observations, so to sort of cut down the wiggle room for the theories, really. So that's what we've been doing, and that's what we'll continue to do. So this is now the next phase of what happened after that initial 40 or so supernovae. There were some very large surveys carried out on the Canada, France, Hawaii telescope and CTIO, which is the same one we used before, but now observing for much longer. So just repeating the same area of sky over and over again and building up huge samples of supernovae as you do it. So you can use the same observations as kind of follow-up of previous supernovae and to find new ones. So this is a very efficient way of working. I won't have time to explain that graph really, but just take my word for it. This just basically churns out supernovae every few days by repeat observations of large areas of sky. And that got the Hubble diagram that I showed before with about 40 objects into this sort of diagram where we now have 740 objects on it. Again, faint going this way, faint magnitudes going up, redshift to the right. And this line that's fitted through them is the same cosmology fit that we got from the 40 supernovae. So it nicely confirms the results that we got before, but doesn't explain what's actually underlying this explanation. So the lambda, the cosmological constant, fits beautifully again, but we still don't know what's causing it. We still have this 120 orders of magnitude problem compared to any explanation that can be come up with from particle physics. So one of the things that, there's a couple of things we can try now. One is to try and look to higher redshift and maybe see if we can see any sign of changes in dark energy properties with time. Because if we can, then it's not a constant. And that would immediately rule out the cosmological constant explanation. So that would be a big breakthrough. And another thing we can do is try looking in different directions on the sky and see if we can see any differences. Because again, that would mean it's not a constant. So these are two directions that we're trying to go in now. So very quickly, this is some work we've been doing in Lancaster with Saul Perlmutter still in Berkeley and others around Europe and well, the wider world really. A project called Sea Change, where we've been trying to get to the really highest redshifts using the Hubble Space Telescope. And so far, so the idea here is to look for changes then in dark energy as you get to really high redshifts, which correspond to early times in the universe. And we've found about 30 supernovae now with redshifts above 1. So this is pretty much above the limits that we could have got to before. The data's not been all analysed yet, but we've got some nice blinked images to show that we have actually found supernovae. But again, they're very faint little things. It's hard to see them. I don't know if you can even see that on my image. So that's kind of the status with the high redshift end. There are other surveys as well trying to get pushback in time. And the other way of looking at this is to look at in different directions on the sky. And for that, we just need a massive wide area survey that covers kind of the whole sky that you can observe every few nights if we could. And that's where this Rubin Observatory comes in that I showed right at the beginning. This is the artist's impression of the Rubin Observatory. And that the image I showed just now was it under construction, but it really is starting to look like the movie now. It's getting really close and it should start operating within the next couple of years. And so it's going to have something like a 10 square degree field of views. That's very, very large for a telescope this big. And we can't wait really for that to start going. So we were expecting that telescope to be able to produce something like 10,000 supernovae a year, which is a huge number compared to the, we've got roughly 1,000 well-measured supernovae now. So this is going to be massive in terms of statistics and the number of supernovae, and we'll be able to then split the sample up into different directions on the sky and look for differences and see whether the cosmological constant really is the explanation for dark energy. So that's one of the exciting things coming, the Vera Rubin Observatory here on the bottom right, but there are others. Where shall I start? In fact, there's a lot of exciting things coming. So in the middle here, this is the James Webb Space Telescope, which is due to be launched. Actually, they've just fixed the launch date for December this year. It looks like that's going ahead. So that is a very large space telescope. So I say it's large, it's 6.5 meters diameter, which is actually smaller than the largest telescopes we've got on the ground now, but for a space telescope, that is very large. So this will be fantastic for observing very, very faint supernovae, really early times in the universe, a long, long way away. And then we've got Euclid and the Nancy Grace Roman telescope, which are both relatively small space telescopes, but with very wide angle field of view. And again, they'll be great for doing surveys at large distances. They won't be as distant as the James Webb Space Telescope, but they'll have the advantage of the wide area. So great for large numbers of supernovae. And then finally, down the bottom left here, there's a new spectroscopic instrument being built in Chile, which we're involved in Lancaster as well. And that'll be great for getting spectra of all the objects that the Vera Rubin Observatory finds. So we'll be able to measure their redshifts and check the types. So we're going to have this massive sample of supernovae with confirmed types and redshifts that we can use for cosmology. And then finally, the European Extremely Large Telescope is something I've been working on separately from supernovae really, but for quite a long time. And this is going to be a nearly 40-meter diameter telescope that's being built now in Chile. It is under construction. One change I've had to make since the last time I gave a talk like this is the first light date. Unfortunately, it's shifted by a couple of years. It's now 2027. So it is slipping, and obviously COVID has had quite a big impact on the construction here, but it is going ahead, and we're really excited about that. So that will be another telescope that will be great for very large distances and very faint objects. So that will be great for checking whether dark energy is changing with time. And I think that's it. That's all I'm going to say. I'll just leave you with this movie, which I hope will start, of the Extremely Large Telescope on its mountain in Chile. This is the artist's impression of what it'll look like when it's finished. So I've been to the site and seen the sort of hole in the ground as it was then. And I was just amazed. The diameter here at the bottom is enormous. It takes quite a long time to walk all the way around the telescope, and to think that it's going to be as high as it is across, pretty much, it was really something to see. So I hope we'll get some dramatic advances with these telescopes, hopefully some surprises, and perhaps even understand this dark energy. And I'll stop talking there.